Right. It is called, yeah, good question. So it is called entropy satisfying scheme because it it is going to give you an approximation to the solution that satisfies the entropy condition. So by itself, the scheme is not necessarily uh, maybe it is, but I'm not aware of a proof that like this, if you follow the scheme, the numerical entropy in some sense is going to be satisfied. But this is going to give you an approximation to the only physical solution that satisfies the entropy condition. In other words, it gives you approximation to a physical solution where the characteristics does not run away from the shock waves. Yeah. Any other questions? Will information now go from one side to another? Good questions. Okay, so if you have a shock wave, I think the answer is no. So if you have a shock wave moving towards the right, okay, I know I'm taking information from the left, right? If you know your shock wave is moving towards the left, I'm taking information from the right. And if you have a shock wave that runs into each other, then I'm taking information from left or right according to which one is higher. I mean, which one is higher or lower depending on which direction, which case you are looking at. So I'm always looking at the side of the information, the side of the discontinuity where the shock wave is moving from, right? So I'm never taking the value of the flux using the information, using where the information is going towards, where the shock wave is going towards. So the answer to that question is no. The answer to your question gets a little bit more tricky into later part of this lecture where we are doing reconstructions. We are doing like a second order scheme. So I'll if I don't remember to answer your question then please remind me. And to start from our burger solver we constructed last lecture. So in last lecture, let me remind you, we are constructing a Burger's DDT that is supposed to be called by OD45. And in the beginning, we get the number of intervals. It is exactly equal to the length of U because U represents the volume averages. Okay, and F of U bar equal to the Burger's equation flux, where we can change later on to some other equations. And we set this central average scheme is not a very good scheme, right? So we commented that out. Actually, we are going to delete that. And here we are using the first order upwinding scheme to compute the interface flux. So here, let us change that to a Godunov scheme. Okay. So for we have the two cases are according to our PowerPoint slide is if UL is larger or UR is larger. So here instead of looking at this, we are just going to say, okay, if UI minus 1 is greater than UI, okay, then UI interface should be what is that case? So if this is UL greater than UR, it should be the maximum, right? I should be taking the maximum of UF bar I minus 1 FU bar of I, and the Burger's equation is convex. So the maximum always lies at the boundaries. It's impossible for a convex function to have a maximum in the middle of the interval. Okay, that's basically you can prove that by two lines looking at the definition of a convex function. So the other case is I should be taking the minimum. And the minimum can be actually three values. It can be one of these two values or 0, right? Because the minimum of this U squared over 2 function can be at 0 or one of these uh, one of these two ends. So these are the three values I need. Does that work? Mean of, let's see, 1, 2, 0? No, that doesn't work. So, huh? Oh, I can make it a vector. Good. So that'll work. Okay, that'll work. Yeah, thanks for the hint. That's very smart. Yeah, good question. So yeah, so if UL is mm, yes, okay, so that makes sense. And also this is wrong. This is okay, so this is zero only when you have bar only when UI minus one and UI actually encompasses the interval zero. So I shouldn't be taking the minimum of these three things. What I should do is, yeah, okay, else if you, okay, one word, UI minus one is less or equal to zero and, no, and, is that, is that right? Okay, zero is less or equal to UI. Okay, then fu interface I is equal to zero, else this is equal to the minimum of this and that. Okay, is that right? Yeah. Anybody, if you find a bug in my code, please speak up. I would be grateful. That saves a lot of time. I think not, because if UI minus one is, if UL is greater than UR, then we are looking for the maximum. And the maximum doesn't depend on if I cross zero or not. Right? But for general equations, yes. For if you have an equation that is concave, for example, then you need to check that when UL is greater than UR. All right. Good. All right. I think we have it. So, so do we remember what we did? Okay, so let's actually x and u0 is equal to draw function. How do I use draw function? Okay, so x0, 0, 1, let's say 128, u0. So that gives me opportunity to draw a function. So let's actually draw a case where I would get non-physical solutions if I use a upwinding scheme. So this is the case where I should have an expansion wave. The left is going towards the left, right is going towards the right. And now let's start solving using Burger's DDT. So I'm gonna say dt is equal to 0.01. I'm gonna for I goes from 1 to, let's just do 100 steps. I'm gonna say t and u is equal to OD45 Burger's DDT u prime. I think that's right. Just trying to use the history. U is equal to, nope. So okay, u0 is equal to, nope. Okay, u and this, that's right. And what else? I'm going to plot. Oh, I didn't initialize XX. That's fine, I'll do that later. And the draw now. Of course, I didn't initialize XX. XX is equal to that. So I'm going to redo this for loop. Okay, hopefully that'll work. I'm going to close that first. So, so XX is 2 by 120. Oh, okay, so that's the problem. I think my X is more like a finite difference type of X. So what is actually my X? 0 and ends at 1. So let me recompute my x is going to be length space of 0, 1, and 129. Okay, let me do that. So x is equal to that. Okay, so now I think I'm going to work. All right, I think I have a solution that why does the axis goes all the way to the end?